Thanks everyone, in particular, thanks Thomas for inviting me to be here and explain you a bit of our work here in Madrid. The title of my talk is From Complexity Theory to Astrobiology, There and Back Again. And what I want, this talk is gonna be organized in two different parts. In the first one, sorry. Oh, sorry, I thought this chat was for me. The first part of the talk is gonna be like an introduction to the relationship between complexity theory and astrobiology. They seem to be very different things, but actually they're very well connected. And for a long time, they've been very well connected. And the second part of the talk, in case you want me to continue, because perhaps you start asking and we get a debate there, and so we could stop there. But the second part of the talk, which will be about, I don't know, after like 20 minutes, my idea is to explain you a particular work, which is the one that I explained really fast in the nice, I think it was Life and Science conference you organized, because it's a good example of how complexity theory and astrobiology can connect in a synergy. And it's like a particular way of saying, of phasing what I'm going to show you now. So let's start with, who are we? We work at the Centro de Astrobiología. It's an astrobiological center, which is in Madrid, Spain. And well, I'm starting a group there. And right now we are 4 of us. Marina is in the audience. She's starting a PhD, or she will start a PhD in the next months. Sofia Backlund, she's a student from Finland who has come with us to do an Erasmus for some months. And Adrian, who is also in the audience. Actually, he's starting with us next Friday, which is tomorrow, in fact, for a postdoc. And so if any of you want to collaborate and want to come to Madrid or whatever, please contact. And this is my webpage where you can get information about what I like to do professionally. Okay, let's start to talk to you about complexity theory and astrobiology and their connections. Let's go from physics to astrobiology, but through complexity theory. Okay, traditional physics, I don't think there are many physicists in the audience, but still, if you don't know, traditional physics is completely reductionist. What does that mean? It means that we break things, we break systems into very small pieces, and we try to understand each of those pieces. That has worked really, really nicely for the last 200 years. In fact, the Nobel Prize Veltman, expert in particle physics, said 20 years ago, today we believe that everything is made up from elementary particles. Knowing all about them in principle implies knowing all about everything. Okay, this is only true in classical physics because we've been studying very simple problems: particle bodies, particles, bodies, and their interactions. And this has worked really nicely, I know, from quantum theory to astrophysics. But there are many systems that cannot be attacked from this point of view. It's true that physics is based on mathematics, and therefore it's formal and it's quantitative, and that's great because it helps us to do predictions. But unfortunately, biology is too complex. Biology studies how organisms function, work, and how they interact. And the problem is that the simplest interaction in life involves millions, billions of atoms. And so this reductionist way, in most cases, is not very useful to get how to understand how things work in biology. It's true that after the discovery of the structure of DNA 70 years ago, and all the technological and bioinformatics developments that we found that we did later, like these transcriptomics, metagenomics, and all those omics, it is true that we have quantified biology, but we have not formalized it, in the sense that we still don't have real theory about that. And of course, astrobiology suffers from the same limitations. So we need to attack astrobiology from a different point of view, because the problems that we want to solve, especially if we're talking about the origin of life, are far too complex for traditional physics. And that, by the way, please interrupt me whenever you want. So, conclusion, we need something new. And this something new could be, at least in part, complexity theory. In the 70s, like 40, 50 years ago, physics created a new branch, which in fact is, we will see later, that it's like a mixture of different disciplines that already existed. What is a complex system for us? Because you know, complexity and complex systems is a very polysemic word. For us, for physicists, a complex system is a system that is made of lots of elements that interact in a very complex way, in a way that actually, in different at different scales, we can find different properties that we could not predict if each of these parts were studied individually. We need to study complex systems as a whole. At different scales, different behaviors. And we call that emergent processes. A couple of examples, in case any of you had never heard about complex systems. Traffic. I mean, you can be the worldwide expert in how your BMW or your small car works. That information is completely useless if you want to study a traffic jam. Or perhaps you can be an expert in, I don't know, in snow crystals. That information will never explain you when an avalanche is going to happen. So these are the kind of systems that we study, full of little individuals or little organisms or little parts that interact in a very complex way. All right. Actually, many astrobiological systems do fit this definition. And many people, sometimes from the philosophical point of view, others from more of physics point of view, like Stuart Kauffman, have asked themselves if life is an emerging process. I wouldn't know. We're working on that. All right. Let me show you a couple of sketches that I have found in the internet that explain quite well what a complex system is. From a point of view of main disciplines, actually, complex systems, we can't really say that it belongs to physics, because it's related to physics, it's true, but also to mathematics as the formal tools that we use. We also study, of course, transportation, movement of traffic, things like that. Obviously, biology, and this is what we're going to talk about today. Also, economics. I've also worked in economics and sociology. And it is true. So complex systems are very, very, very transdisciplinary. And the tools that we use can be, that's why I love it. We can apply them to very different disciplines and very different problems. From a different point of view, which are really actually the real topics that you're going to work with if you work with complex systems. The first one, well, I start with that one because it's the one that I right now work the most, and the one that I'm going to talk to you about later is complex networks. Nodes connected by links, all right? But also, we are going to study, of course, collective behavior, you know, self-organized criticality, cells that interact, things like that. I love game theory, and it's a very, very useful tool to understand how people, how social groups organize and evolve. It came from mathematics, but now we are applying it to sociology. Of course, nonlinear dynamics, which is mathematics that study the evolution of systems. Systems theory, when we attack the complexity from a computational point of view. I have never worked in that subject, actually. Pattern formation, there are many people working on how different patterns appear in life, for example, or in, I don't know, for example, when you study bacteria and how they grow, all that kind of study is based on pattern formation. And finally, last but not least, evolution and adaptation. Actually, I studied astrophysics a long time ago, but well, I did my PhD in chaos theory, and now I'm working in, well, from there, I went into biology, and I studied virus evolution and stuff like that. Then I went into economy and sociology. Now I'm in astrobiology. So actually, of all this, I have actually the last 20 years, I've been working with networks, collective behavior, game theory, nonlinear dynamics, pattern formation a little, and a lot of evolution. So if there are students in the audience or other people that could listen to this talk in the future, if you want to find a discipline in which you can use very different tools and study very, very different subjects, complexity theory is a good choice. Okay, then. Let's focus on complex networks. Complex networks can be found in lots of different places and different scales. A complex network is just a group of nodes connected by a group of links. That's a network. We can find it in the microscopic scale, like protein networks or RNA Neutral networks. This Neutral network was studied by me like 10 years ago. An RNA Neutral network is a network in which all the sequences, all the nodes represent sequences that fall in the same structure. So we could say that if we think that the structure is like a proxy for function, it would be all the nodes, all the sequences that have the same function. And two nodes are connected if they differ only in one nucleotide. Obviously, each biological network has a different meaning, but this is an example. Okay, 10 years ago, Carr and company were able to organize the whole cell as a network. And of course, at a bigger scale, the biological network, the most important biological network is obviously the neural network, 100,000, around 100,000 million neurons connected. And many of them are connected to more than 1 million other 1 million other neurons. So imagine the complexity of a brain. We obviously have no idea of how the brains work from the point of view of network theory. We still have to do a very, very long way there. In another scale, we have people, social networks. A social network is a network where the nodes are people. And these are three networks that I studied not long ago. Each of them are a small village in India, and we studied how these three villages should connect to be more stable, more economically stable. And of course, if we go to a new scale, we have the global social network, 7,000 million people connected in a very, very, very complex way. So we have networks at all the scales. Let me show you a funny story. Let me tell you a funny story about this local social network. Okay, we published this work 5 years ago in Nature Communications, and the name of the work was Competition Among Networks Highlights the Power of the Weak. What we found is that, let me go back here. Dan, I don't see if you see I don't know if you see my arrow there. I hope so. It was very funny that it was curious that we found out that when three different structures like villages or companies try to interact, in many cases, it is much better for all of them actually that the weak ones connect instead of connecting to the strong one, so that the collaboration of the weak structures sometimes is very, very efficient. This was our result. As you can imagine, in this case, it was something easy to be sold by the newspapers. And especially in South America, there were many, many newspapers that talked about this. And let me just show you, actually it was in Spanish, but I translated them. Let me show you this typical thing that we could find in the newspapers that were completely surprised, like people with shorts and saying scientists prove that the power of the weak is in cooperation. This Indian women here or these people like in this photograph, I guess it's must be the southeast of Asia, things like that, saying that the mathematicians, here mathematics reinforce the underdogs of society, And the best point of all this, which is quite funny, is that, here in this case, and this is this newspaper is this is the Europa Press, which is the most important news company. They wrote they talked about our work on. Here, Derechos Humanos means human rights, with other human rights news. No? So, as you can imagine, as Thomas knows, and all of you must know, sometimes you find you cannot control what people say about your work, especially in newspapers. But this, I found that it was funny. So, let me show you where are the connections between complexity theory and astrobiology. A couple of years ago, I decided to read the next astrobiology strategy from 2015 to 2025, which I suppose that Thomas and others of you might know. And I found out that there were many more connections to complexity than I expected. For example, in the point 3, which is called early life and increasing complexity, I could find that my work could be actually very, very well connected to the origin and dynamics of evolutionary processes, because they are talking about theory, fundamental innovations in earliest life, and the fourth step, which is dynamics of the subsequent evolution of life. In particular, actually, it's a quite nice strategy because they give very clear questions of subjects that they think that NASA thinks that should be worked on. In the subjects of evolutionary context, in the rating evolution, they are very interested in understanding the relationship between genotype and phenotype. And this is the case I told you about before with this RNA Neutral Network. Each of the nodes is the genotype, and the whole network is the phenotype. They also want people to study the influence of environmental conditions on evolution. And this is what I've been doing for a long time. Whenever you have this RNA Neutral Network or something similar, you can change the conditions and you can see how the populations move on the network. Regarding evolvability, a couple of questions that they say: how do evolutionary innovations originate, or how do evolvable chemical systems arise from non-evolvable chemical systems? This is what I'm going to talk to you after in a few minutes. And finally, an important question: how are fitness landscapes? The classical theory of the 30s of the 20th century, it was very important and very useful for 100 years, but now we know that fitness landscapes have nothing to do with those typical hills that Fisher and Wright used to talk 100 years ago. And I've been also working on that. But in particular, let me finish with that sentence regarding networks. They say, let me read it: interaction networks are central to life. Molecular interactions, genetic interactions, epistasis, metabolic networks, ecological networks, all of them are examples of the importance of network structure and architecture in living systems. And so this, and the main sentence is, while we may understand the parts of life, we know relatively little about their interactions. And this is the main take-home message of today. We know very well, actually, thanks to biologists and chemists, how do the parts of life work, but we don't really know very much about those interactions. And this is what we're doing. Okay, let me show you. Let me show you a few ideas of what we are trying to do. We're trying to develop a theory of evolutionary competition or interaction in complex astrobiological processes. We have two ideas, two targets. The first one is to develop a theoretical framework to analyze processes, astrobiological processes, in which different agents that are organized as networks fight or compete for resources, okay? This is the first idea. And we have called this theory the theory of competing or of interacting networks, if you want. But then we want to apply this theory, which is I've been developing it since 2013. So now it works quite nicely. We're trying to apply it to problems of astrobiological interest, such as viral and RNA evolution, the origin and early evolution of life, but also socioeconomical systems and any others that could be of interest for us. All right. Oh, I'm trying to make this disappear. Okay. What is competition? Okay, competitive interactions are everywhere. Actually, they are the driving forces behind evolution, but also not only in biological systems, also in sociology, also in technology. Actually, not all of them, of course, but many of these systems are organized as complex networks. And an example is, I don't know if you're seeing this thing here, because can you see well the
competition as the essence of evolution?
So you're not
seeing wolves.
You can
read
I
see dolphins.
And you can read the title.
Yeah.
Oh, sorry, because I have something here which I don't know how to. I guess it will disappear. I'm sorry. Okay, then. Well, I'm sorry for this A, which is an E. Okay, let's see a competition from our point of view. Many structures compete. Firms in a market economy compete for customers, obviously. Web pages compete for absorbing the largest possible number of internets. For example, here we have this complex network, which is a very nice political blogosphere in the sense that blues are Democrats, reds are conservatives, and we can see that they are like two networks in connection. This is what we are doing. We are studying networks in interconnection. For example, this one, which is a network that we studied in this paper a few years ago, is our friendship network of dolphins. Each node is a dolphin, and two nodes are connected if these dolphins are like friends. They stay more time than average together. And we can see that they clearly have two different networks, females and males. Okay, then. And we found out around 8 years ago that no one had studied these competitions between networks from this point of view. And so we have developed, as I told you, this strategy based on networks that interconnect or that interact. This is what we are interested in. Just to finish this part, so we have this theory of interacting networks. It's based on theory, on algebra and applied mathematics, but also on real phenomenology. It's connected to physics, mainly on complex networks, nonlinear dynamics, and statistical mechanics, but also we try to apply it to astrobiology, and in particular, molecular evolution, astrochemistry, and systems biology. Okay, which are our tools? We don't really work, we don't do experiments, okay? Because I'm really bad at that. But we work with people who do experiments. So we do theoretical work and we do numerical work, and we get real data and we study it. So this is more or less what we do in our group. Okay, now I'm finished.